This is the lecture from chapter 5, and we are going to be learning more and more information as we proceed through the course that you can use to determine information about your processes. So basically the line on the degree of freedom analysis, other equations that relate unknown variables on the flowchart, that is what we're going to be adding to from here forward. So you're familiar with the ideal gas law, and in our book, specific volume is given a hat, and that hat means that we're taking the number of moles, we're taking V divided by N, and that's what the V hat is. So we calculate the ideal gas volume of a gas by simply the relation RT over P. And when can you consider gases to be ideal in this course? We learned that rule of thumb, that and we'll review it. But for this course, basically every gas we are going to deal with is ideal. And these are some gas law relations. So this is a figure showing the pressure, temperature, behavior of a fluid, a pure fluid, a pure substance, okay? And when we know where the critical point is here, C, we know where the triple point is here, and we are familiar with this curve, which represents the vapor-liquid equilibrium line, and this one here is the liquid-solid equilibrium line, and this one here is the solid-vapor equilibrium line. And if you are above the critical pressure and temperature, we have a supercritical fluid. If we are below the critical pressure but above the critical temperature, we have a gas. And if we are below both the critical pressure and temperature but we have a vapor phase, then that's what it's called, a vapor. Okay, that's just kind of semantics. We generally don't know exactly when we look at the information where it stands, so we just call gases and vapors, we call them that a little bit interchangeably. But so we're going to be spending a lot of time on this line in chapter 6 and this line. We don't do much in this class with this line. But anyway, for this portion of the chapter 5, we're going to be spending time here. Okay, let's do an example calculation. I mean, this is just showing you the types of calculations that you will have to do using gas information. And basically what it boils down to is that if you are given information about pressure and temperature, then you can determine the volume if you know the number of moles. And you may need to use that information to determine the number of moles, or use the number of moles to determine the volume. So it's simply applying the ideal gas equation. And you know how to do that because you learned it already in chemistry. So in this case, we have a mole of methane being fed. We know we have 30% excess air, so we can determine immediately the number of moles of oxygen and nitrogen we need. And from that information, we can determine the volume using the given values of pressure and temperature. So be careful always to convert temperatures and pressure, or convert pressures to values where we have an ideal gas R value available. And something else of interest here is that all ideal gases have the same specific volume, which is 22.4 liters per mole at the same temperature and pressure. If it is indeed an ideal gas, it will obey that rule. Okay, so a mass flow controller is an instrument that will deliver gas in a volumetric flow rate specified at standard conditions. So here, this is information that is useful to you. You may not use it much until you start having lab classes. But if a mass flow controller is set to deliver 5 slipum in a 25°C room, how many moles of gas is that? Well, we take the 5 liters per minute, and we multiply it by the standard volumetric specific volume, and then we correct it for temperature. So the standard value is at 273, but we're actually at 298, so that gives us 0.244 moles per minute. So next we can look at if we have mixtures of ideal gases. In this case, we have 5 moles of hydrogen and 5 moles of CO coming together, mixing, and the temperature is 273 Kelvin and pressure is 101.3. So we're going to compute the volume out, right, using R times T divided by P. And here we have 10 moles. So 22.4 liters per mole times 10 moles is equal to 224 liters. So now we can compute the volume fraction of CO, and this is something that confuses students. But remember, if we have ideal gas law, the volume fraction of the gas is the same as the mole fraction. Okay, so that's important for you to remember. So we're going to compute the mole fraction. It's the same. The mole fraction and the volume fraction are the same for ideal gas. So try to remember that. All right, compute the partial pressure of CO. So the partial pressure is equal to the mole fraction times the pressure. So we multiply 0.5 times the pressure and we get 0.5005 bar. So the sum of the mole fractions is equal to 1. Then the sum of partial pressures sums to the total pressure. Okay, so now let's do a calculation. So let's read this together, and then I would urge you to turn off the video and try to solve the problem on your own, and then watch the solution so you see how it compares with the one that you did. All right, so we have a stream of liquid, pentane liquid, flowing at a rate of 50.4 liters per minute into a heating chamber where it evaporates into a stream of air, 15% in excess of the amount needed to burn the pentane completely. So this 15% excess air applies to the pentane. And we've already learned how to calculate this air excess, okay? All right, so the temperature and gauge pressure of the entering air are 336 Kelvin and 208.6 kilopascals. Remember what we have to do with the gauge pressure. We have to add the atmospheric pressure to get the absolute pressure. Okay, the heated gas flows into a combustion furnace in which a fraction of the pentane is burned. So not all of it is burned. So now we know that there's pentane in the product. The product gas, which contains all the unreacted pentane and no CO. What does that mean? No CO? Then it's all CO2. Goes to a condenser in which both the water formed in the furnace and the unreacted pentane are liquefied. The uncondensed gas leaves the condenser at 275 Kelvin and 1 atmosphere absolute. The liquid condensate is separated into its components and the flow rate of the pentane is measured and found to be, okay, so we're going to use this, we're going to convert it to moles, and we're going to figure out what the amount of unreacted pentane is. And we'll use that to look at our conversion. Okay, so your first part is draw and label the flow chart, perform the degree of freedom analysis around the heater, combustion chamber, and condenser units. Okay, and then calculate the fractional conversion of pentane, volumetric flow rates of the feed air, the gas leaving the condenser, and liquid condensate before its components are separated. So here's our flow chart. We have this pentane going in, given in liters per minute. We have air. We know that it's 15% excess, and we have information about the temperature and pressure. So we can determine immediately the number of moles of air, and we will just use that to determine the volume, which is a question later. Okay, and then, so we're heating it here, so no reaction yet. So together we have the pentane and this 15% excess air, and this combusts, and we have coming out pentane, oxygen, CO2, N2, and water. No CO because that information is given to us. It condenses, and we have all the pentane and water. Okay. Well, there must be a further separation. But anyway, the pentane and the water go in one side, and these are the gases that go oxygen, CO2, and N2. Okay, so degree of freedom analysis. Around the heater, we have 3 unknown variables labeled here, which ones they are. And we also know we have the ideal gas, we have 15% excess air, and we have the liters of pentane entering. So we can solve everything around the heater. Without these, okay, then if we were to look at the combustion chamber, we have 7 unknowns, 3 independent atomic species balances, 1 molecular species on inert, and nothing else. So that gives us 3 remaining degrees of freedom. Okay, the condenser, we have 5 unknown variables, and we have 3 atomic species balances, 1 inert, 1 other, and this is our mass of pentane coming out. So around the condenser, we also have 0 degrees of freedom. So let's solve around the heater, okay? We'll start with the heater. We have, we're going to convert the liters of pentane into moles of pentane. And then we can convert, we can use that information to determine, we have 15% excess air. So we have 19.28 kilomoles of air per minute. Okay, in pentane, be sure and write your chemical reaction properly. You need 8 moles of oxygen per mole of P to get you that theoretical oxygen. And we have 19.28 kilomoles of air per minute, which is equal to N2. Then, while we're here, we can also do the balance around the condenser. We're going to find out how much moles of pentane is coming out. We take the mass, divide by the molecular weight, and we have 0.044 kilomoles per minute. Okay, now around the combustion chamber, we can solve the remaining unknowns using carbon balance. Okay, so we have carbon going in the pentane, carbon coming out in the pentane, and we have CO2. So we can calculate the CO2, the nitrogen balance. Nitrogen in is equal to nitrogen out. We know the kmoles. We have 0.79 kmoles of nitrogen per kmole of air, and we have 15.6 kmoles of nitrogen. The hydrogen balance, we have hydrogen coming in the pentane, we have hydrogen coming out in the pentane, and we have water. So we can then solve for water. If we do the oxygen balance, we will find the unreacted oxygen that's flowing out. And that's what we did. Okay. And, okay, so N4 looks like it's 0.88. This is the nitrogen, and this is the air. No, sorry. This is CO2. Okay, yeah. All right, so we have this much moles of gas coming out, and we can calculate the volume of gas using the ideal gas law. Moles of gas times RT divided by P, and choose the proper value of the gas constant, and be sure and put the temperature in absolute, and we solve for the volumetric flow rate of the gas out. And we can do the similar calculation on the volume of air fed. Okay, so to summarize this lecture, the density of a gas can be determined if you know the T, P, and N for the gas. And this is a review from before, but if we have RT over P is equal to 5 liters per mole for any diatomic gas, greater than or equal 5 moles per liter, then it's an ideal gas. And for any other gas, that value should be 20. All right, so here's your video quiz, and I have posted this up. I didn't post this, you don't need to do this. Okay. Okay, so we have two chemical reactions. Chlorobenzene is produced. Okay, when this word is produced, it's the product of the chemical reaction. And this is the desired product. Okay, commercially by the direct catalytic chlorination of benzene. Here's benzene and chlorine. And here's the temperature and pressure. In the process, dichlorobenzene is generated as a co-product. So some of our desired product is further modified and made into dichlorobenzene. So we have liquid and gas streams leaving the reactor. The liquid contains chlorobenzene and dichlorobenzene, and as well as unreacted B. The gas, which is sent to a treatment facility, contains 92% weight per volume HCl, which is a product of the reaction, and 8% unreacted chlorine Cl2. Okay, so you now have enough information to do the balance on this process to determine the volume of gas that leaves the reactor. So it looks to me like you have to choose a basis for this. So I will, let me just take a quick peek here because I think, oops. Looks like it stopped recording. Darn, I need to do that. No, there's nothing else. I see. Okay. All right, let's just see if we can.